Welcome to lab number 4. So this is our last lab for the class. Woohoo. And we're going to be looking at a refrigeration cycle in this lab. So our primary objective here is we're going to be operating a refrigeration system. And the apparatus that we're going to use in this experiment is an Armfield system. So the model number is given to you right there. It's in the back of the room. It's a water-cooled single evaporator refrigeration / air conditioning learning system. And so I'd like to point out the unit is actually labeled really nicely, but I'm just going to point out, kind of highlight the different pieces of the equipment on the left with the refrigeration cycle schematic that we're used to seeing from class. So starting at state 1 here, we first flow our refrigerant into a compressor. So our compressor is sitting back here. So this is our compressor. All right, so that is this guy. Here from the compressor, we go to the condenser. And our condenser is right here on the front face. So this piece right here is our condenser. From the condenser, we go to the expansion valve, which is right here. And then from the expansion valve, we go to an evaporator. So our evaporator is also on the front. It's this piece right here to the right. And I forgot to write a couple things down. So this is our evaporator. And then this is our expansion valve. Okay. Also to connect with kind of what the fluid is doing, the working fluid is doing as it goes through this cycle, back to what we've talked about in class. Here I have a pH diagram for our 134A. So this is our 134A. That's the working fluid inside of our refrigerant system or our refrigerator system. And so the points 1, 2, 3, 4 here all represent the same points as on our schematic up top. So just to remind you, this is our vapor dome. All right, so when we're at state 1, we are starting in a superheated vapor state. All right, because we're to the right of that saturated vapor curve. As we pass through the compressor, we're going to input work into our system. So we have W dot in. And then we get to state 2, which has increased enthalpy and increased pressure. We're still a superheated vapor. Okay. Then when we go through the condenser, we are losing heat. So we have Q dot out. And we're going to decrease our enthalpy here, but keep our pressure the same. So we have this horizontal line that goes from 2 to 3. So we're decreasing enthalpy. And we are also passing from a superheated vapor through the vapor dome over to a compressed liquid. Okay, so over here, we are compressed liquid. All right, and then as we go through the expansion valve, we are keeping our enthalpy constant, and we're going to talk about why that might be in just a little bit. And we're decreasing our pressure. So we're going to decrease our pressure until we get to state 4, which will generally be inside the vapor dome. So this is a mixture. And note that H3 equals H4 here. And then last but not least, we're going to input heat into the system through the evaporator. So we have Q dot in. And at constant pressure, we're adding heat, and then we're gonna move from our mixture state back to a superheated vapor. Okay, so this is generally how the system works. Hopefully it looks very familiar from what we've seen in class. And in addition, so I have this schematic here on the notes. I actually kind of like the one that's on the placard on the refrigeration unit. I think it's a little cleaner, but I just wanted to kind of show you how the system works. So we have our 134A inside of our refrigeration cycle. So our 134A, I'm going to show in pink. The colors of the lines on the schematic change with like the state that it's doing through the loop. But essentially everything in here, starting with our compressor. So if we start at 0.1, we go through our compressor, into our condenser, over to a receiver and a filter, and then through our expansion valve here, and then through the evaporator and back to 0.1. So this is all a closed loop that the working fluid of R134A is contained inside of. In addition to this, though, the system also has 2 loops for water. So there is a water reservoir, which is the big kind of tank that everything is sitting on top of. So that is a reservoir of water. And inside of there are 2 pumps. And those pumps are going to take water and pump it through on the right-hand side through the evaporator. All right, so it's going to be exchanging heat with the refrigerant in the evaporator, and then we're doing the same thing on the condenser side as well. So we're cycling water through both the evaporator and the condenser. Now note that the refrigerant and the water do not mix, but the evaporator and condenser are acting as heat exchangers in this way, okay? So this is the setup of the system. And I was gonna do theory first and then show you the unit. And that's what I did last night. But today I'm gonna do it a little bit differently because it takes like 30 minutes for the refrigeration cycle to get to a steady state. So I'm gonna show you how to set it up and start it running. I'll get it started. And if you wanna periodically look over at what the plot is doing, you can do that. And then we'll do theory while we wait. So let's do that. Okay. Okay, so in this lab, we're going to be using the computer and a data acquisition system for some of our data collection, and then we're also going to be using some analog gauges on the system itself. So the first thing you're going to want to do when you come to the lab is log in. There's a paper here that tells you the username and password. No. If you can type correctly, it works. Okay, and then I checked, I can't zoom in on this screen anymore than this, unfortunately. So it's a little bit of an eye chart. But to open up the software, there's just an icon on the desktop called Armfield Refrigeration, and then the name of the model number. So just click on that and it'll open this. All right, so this will show you essentially a simplified schematic of our refrigeration system. So everything in red is the R134A. And then it's showing it go through the compressor, the condenser, the expansion valve, and the evaporator. And then there's also some data here for the water that goes through the evaporator as well as the condenser. Okay. So the first thing that you're going to want to do is check if the computer and the system are talking to each other. If it is, down here, it'll say IFD VCOM and it'll give you a number. Right now it's reading 4. It should always be 4, I believe. If it says like not found or doesn't list a number, you'll click on the red telephone and then select channel 4. And then it should say this, and that means you're communicating. The other thing I want to check is on the back side of the unit. There are 2 lights, so there's one for power on and one for active. You're going to want to see both of those illuminated. And so if you have issues with that, it's generally kind of good practice to just turn everything off and then back on again and try again. So to turn, I've already done it, so I won't do it again, but to turn this on, you flip the switch to the I. So there's a 0 or an O and an I on here. I means on, O is off. And yes, okay, so everything is all connected and communicating. So the first thing that we're gonna do is we're gonna turn both of our pumps on to 100%. So there's pump number 1 and pump number 2. These are for the water. So I'm gonna do that now. So I'm gonna type in 100 and hit enter, and you can hear it turn on there. I'm gonna do the same thing for the second pump. And there, the second pump's on. And then the next thing I'm gonna do is there's a little toggle button for compressor on. I'm gonna turn the compressor on. And I'm going to increase its percentage to 50%. You can hear it turn on there. I'm gonna put it to 50% for right now. The specific percentage that you want to do is going to be in your lab handout. So follow that when you're in the lab. And then you'll notice that all of these values are going to be updating live. So you have the Q in listed here, Q out here, and a bunch of temperatures listed over here as well. One thing that is kind of a little bit hard to see because it's grayed out, it looks like a button. There's a flow rate here, so if you click on it, it'll let you put in a number. Basically what you have to do is you have to come over to this flow meter right here. So this one acts in the exact same way as we've seen all of our rotometers in this class. So you're just going to read it from the top of the little kind of spinny thing in here. And you can see that, well, maybe you can't from there, but it's kind of settling down to a speed. So wait until that stops moving. And then you'll want to periodically update what the flow rate is on the computer. So as this is running for probably about 30 minutes, every few minutes, update what the flow rate is in there. So right now we're at like 21 and a half. So I'm going to type in 21.5. Also, don't panic. This button will round to the nearest 1 digit. So I put in 21.5. It says 22 now. So that it's fine. That's just what it does. Okay. So the next thing that we want to do is we want to look at what our data is doing. So I'm going to click on this view graph. And then I'm going to go to, I want to add channels to this. So I will click on format, and then I will click on graph data. All right, and so I am going to select the temperature channels for 3, 4, 5, 6, and 7. So I can select all of them by holding onto the control button. So 3, 4, 5, 6, and 7. Oops. And then I am going to click the right arrow to move them onto my y-axis. So these are all going to plot on the same y-axis. And then on the x-axis, I want to do elapsed time. So it defaults to sample number, switch it to time. And then I will say, okay. And then once I have that loaded, I'm going to click go. So this is going to start recording my temperatures. So I have one set of data so far, and it will, as it goes, it's going to add more. So there's more. All right, so I am going to let this run, and then we're going to talk about theory. And if you want to just glance over here every once in a while and see what this plot starts looking like, I'll try to remind you as we go. But there we go. Okay, so in this lab, we're doing experiments on a refrigeration system. So we are essentially wanting to calculate coefficient of performance and capacity for the refrigerator. And so in order to do that, we're going to apply conservation of mass and energy to each of the devices in the cycle. So very similar to what we've done in class, except for now we're measuring the quantities rather than just getting them handed to us in a problem. Okay. So let's first, since I have the equations written down for us here, let's first talk about what sorts of assumptions that we can make in general for this system. Any ideas? Yeah, so this is a steady flow. All right, so this means that our time derivatives are 0. So that means I can get rid of this and this. Anything else? Is there anything we might be able to neglect? Yeah, so we're gonna neglect kinetic and potential energy. So that means I can get rid of these terms in my energy equation. And then the one last thing that it's not really an assumption, it's just a simplification here. All of the devices in our cycle are one inlet, one outlet. So I can get rid of these summations because we always have just one in and one out. So we're just summing over one. So one inlet, one outlet means that I can get rid of these summations. All right, and so that means that our conservation of mass just says that 0 is equal to m dot in minus m dot exit, or m dot I is equal to m dot E, which is just some mass flow rate m dot. Okay. Okay, and our conservation of energy equation is just 0 is equal to q dot CV minus w dot CV plus m dot HI minus HE, right? And remember, q dot for the control volume is always q dot in minus q dot out. And w dot for our control volume is always w dot out minus w dot in, right? I'm afraid nothing that exciting has happened yet, but we have lots more data points. Okay, so these are our starting place for the analysis that we're going to do on each of the devices in the cycle. There are 4 of them. So let's have a look at that real quick. So first of all, I'm going to simplify this just how I did before. So we got rid of our time derivative. Trying to keep the colors the same, which I already did not. So steady means the time derivative goes away. We're neglecting kinetic and potential energy. And we are also getting rid of our summation, and we have that one flow rate. All right, so we get rid of these as well. Okay, so for our evaporator, what we have is 0 is equal to q dot CV, which is just q dot in minus q dot out, minus our w dot CV, which is w dot in minus w dot, I'm sorry, w dot out minus w dot in. Right? And then we have plus our mass flow rate times the difference in enthalpy between the inlet and the exit. Okay. Okay, so for an evaporator, and I'm going to just copy and paste this schematic because I think it's helpful to reference. You don't have to do this. You can flip back and forth if you want. But I'm gonna just pop this here. All right, so for our evaporator, which is this bottom one here, do we have any work terms to worry about? No, right? So there's no work for our evaporator. So I am going to get rid of these. So we have no work. What about Q dot? We just have an inlet Q dot, right? So we have no Q dot out. All right, so our governing equation just becomes that 0 is equal to Q dot in plus M dot HI minus HE. Right? Okay. So this is our essentially our simplified governing equation for our evaporator. You will use that in your analysis. Now let's look at our condenser. So our condenser is this top one here. So we essentially have a similar thing as the evaporator, but it's kind of working in reverse. So instead of Q dot coming in, we just have Q dot coming out. Still no work, right? So because of that, I'm going to get rid of work. So we still have no work. And Q dot CV, we have Q dot in minus Q dot out. All right, but we have no Q dot in this time, right? So our governing equation becomes 0 is equal to minus Q dot out plus M dot and the difference times the difference in enthalpy. All right, and then this is our governing equation for the condenser. Any questions so far? Feels okay? Okay. Great. So for the valve, that is this guy over here on the left. Do we have any work or heat transfer terms? No. No work or heat transfer terms, so that means that I can get rid of both Q dot and W dot in this equation. So no Q dot or W dot, which means that this equation just becomes 0 is equal to M dot HI minus HE. M dot's not 0, so I can divide through by it, and that means that HI is equal to HE. If you remember, I just told you, I made a statement saying that at the valve, our enthalpy stays constant, and I was going to tell you why. This is why. All right. So we have this as our governing equation here. Okay. And then last but not least, we have our compressor. So our compressor is in the red box over here on the right. So we don't have any heat transfer for this one, but we do have work coming in, right? So let's make those modifications. So no Q dot. But we do have work in. So W dot CV is equal to Q dot out minus Q dot in. We don't have any W dot out, so that means our equation is just 0 minus negative WCV, which is minus W dot in, plus M dot difference in enthalpy again. All right, so this is just 0 is equal to W dot in plus M dot HI minus HE. Oh no, the screen turned off. Oh, something. That's very climactic. Okay. All right. So you can see things are happening. That's good. But real quick before we go on, I've left all of these equations in terms of ins and out subscripts. Since we're looking at a bunch of different devices and we've kind of numbered the cycle from 1 through 4, I'm going to make note of how HI and HE are connected to the 1, 2, 3, and 4 states. Okay. So let's look at our evaporator again. So our inlet for our evaporator is going to be over here. So we're starting at state 4 and we end at state 1. So the inlet is H4 and the exit is H1. Does that make sense to everybody? The condenser, we go in at state 2 and we leave at state 3. So inlet is state 2, so H2, and then we leave at H3. Next one is the valve. So for this valve, we're coming in at state 3 and leaving at state 4. So we have H3 and H4. And then last but not least, we have our compressor. So we're coming in at state 1 and we're leaving at state 2. So this is H1 and this is H2. Okay. Any questions on these governing equations? Simplifications, anything? Okay, cool. The other thing that the equation that you'll need, this is in the notes, of course, for class, but we want to figure out the coefficient of performance. So we will need to use the following. So COP for a refrigeration unit is Q dot where did I put it? Q dot N over W dot N. Okay. And in addition to that, we're also going to calculate the capacity in tons. And so you'll just need to keep this unit conversion handy. So 1 ton of refrigeration is 12,000 BTUs per hour. Okay. So for this lab, you're going to need to generate a pH diagram. All right, so essentially we want to see the refrigeration cycle from this equipment on a diagram that looks like this. Though it'll look a little less stretched out compared to the one that I drew first. So it'll look something like this. So you're gonna want to calculate your enthalpies at each of the states 1, 2, 3, and 4. And then you can connect them with lines based on the cycle direction, right? So we always go from 1 to 2 to 3 to 4 and then back. And then make sure on here that you put in the saturated liquid and saturated vapor lines. So these are from the textbook. Saturated vapor line is this orange one here, and then the saturated liquid line is the blue. Okay. Okay. Few comments on the discussion. So in this lab report, we would like you to summarize and research the typical coefficients of performance for refrigeration and AC systems. So have a look at those typical values, both for residential and commercial applications, and then compare with what those values are to what you measured in the lab. Of course, make sure you provide your references. In addition, we would like you to research and summarize information on the difference between 3 different classes of refrigerants. So they are CFCs, HFCFs, and HFCs. First thing we want to know is what do these stand for? So I will not tell you now. What are the pros and cons of each of these? What types of applications are they typically used for? And which type is generally used for automotive applications? Okay, and then last but not least, we'd like you to discuss the practical purpose of having the receiver and the filter in the system design. So these 2 elements are right before the expansion valve. So they're called out on the system, and you can have a look at those. And then, bless you, I've included kind of step-by-step instructions on running this. This is what I already walked through earlier. So you can see that this is perfect timing, you guys. Okay, so it's starting to level off that yellow curve. So that yellow curve is the compressor temperature. I think it's T4. All right, so that one is going to take the longest to get to steady state. So once that one stops changing with time, then you can take all of your steady state data. All right, so I have included some tables in here for doing that. You're going to want to make sure that you have recorded all of the temperatures and the pressures and flow rates, and then you can calculate your enthalpy using the tables. So you'll be collecting temperatures and pressures, so you can use tables to figure out enthalpy. Hopefully you're all old pros at doing that by this point. And then you can calculate your Q dots and W dots to find coefficient of performance and capacity. Couple of other small things that I want to draw your attention to. So make sure that your state 1. So if you remember, our state 1 is right before we head into the compressor. We want to have a superheated vapor. So we want to make sure that our refrigeration system here is in a superheated vapor state at state 1. So you will have to check the pressure and the temperature at state 1, and then either use the tables in the book for our 134A, or you can use this chart. So this is a little bit different presentation of the same data that we've shown in class. So I'm just going to walk you through this one real quick. So what we have here is we have pressure on the vertical axis, 2 different units left to right, but they're both pressure. And then we have enthalpy on our horizontal axis. We have our same vapor dome here that we're used to seeing. So this is our vapor dome. All right, and it has called out kind of in tiny little text, the critical point, and then the separation between saturated liquid and saturated vapor. And then there's a bunch of other lines in here. All right, so outside of the vapor dome, these lines go with temperature. So since you have pressure and temperature, that's what I'm going to draw your attention to in particular. So if, for example, we had a temperature of 110 Celsius, then we are looking at this temperature line or isotherm on this chart. All right, so our enthalpy is going to be figured out by following this curve around and figuring out where it intersects with the pressure that we've measured. Okay, so if, for example, I was measuring 1 megapascals of pressure, I would just take a ruler and figure out where it this straight line intersects with my temperature isotherm, and then draw this down to here if I wanted to find enthalpy. So this would be H that I would measure. But for the lab, you just want to make sure that the intersection of the pressure and your temperature is somewhere in this superheated vapor region. Okay, and then you're good. Questions on reading this one? You can also use the charts if you feel more comfortable with that. This is all the same information as what's in the charts. Okay. Okay, a couple other comments. By the system over here. So oh, it just went to sleep again, didn't it? Okay. Okay, so okay, so T4 is the one that's going to take the longest to get to steady state. So it's not actually quite there yet. Once this flattens out, which I guess we're probably approaching 30 minutes that this has been on, you should start to see this really level off. I wouldn't call this steady just yet, so I would wait a few more minutes, like if you were actually in the lab at the moment. So let's talk about the things that you want to take note of that are on the apparatus. So there are 4 pressure gauges on here. There's little pieces of tape on 2 of them to tell you that they're P3 and P4. All right, so these ones are for the R134A. And then we also have these pressure gauges for the water side. Okay, be careful with the units. So this one is reading in bars. And same with this one. So these two are the same style and these two are the same style. And then this one you can read in PSI. Okay, so just be careful with your units. Make sure you note down what unit each of the units that you're reading are. And oh, you know what? And also this has settled down. So this is around 20. I'm gonna go back. If you want to go back to the schematic, you click this button. So any of the buttons along the top here, you can just hover the cursor over top of it and it'll tell you like the word description of what it is. So I'm gonna put this in at 20 because it's settled down to 20. I can go back to my graph. And let me see. Oh, you'll also need atmospheric pressure for your calculations because all of those pressures there are gauged, but we need to know absolute pressure. And so you'll need to make note of the atmospheric pressure in the room using this barometer. So don't forget to do that. And yes, okay, so last thing to explain here is you're gonna want to save your data. So go to this little table icon. So if you go to view table, it will show you all of your data like an Excel sheet. And you're just gonna export this as an Excel spreadsheet. So save as, and then, you know, save it however you want. Make sure you drop down and pick the Excel format. And then save it. You can email it to yourself or bring a flash drive or however you wanna do that. And make sure that you know, do that once this has gotten to a full steady state, okay? So once you're done with that, you can stop recording with the little stop button up here, and then go back to the schematic, and you are going to turn off everything in the same order that you turned it on. So I believe we did, we're gonna turn off the compressor first. So I'm going to take down the speed slowly using the little toggle buttons. All right, and then I'll turn the compressor off, and then I'm gonna also turn off the pumps. All right, that's one pump, and then silence. Okay. It didn't seem that loud until just now. All right, so now it's off, and then you can just close down this experiment. It'll make sure, it'll send you a notification if you didn't save the data, so just make sure you save the data before you exit, say okay. And then, you know, you can log out of the computer and then turn off the system. And that's it. Any questions? Yeah.
I guess, are we using the graph that's provided in that? Or no?
So it will not like export the graph itself. It'll give you the raw data. So and I can't remember exact, I don't think you actually have to make that plot in the lab report, but
Okay.
double check. I don't think you have to. We just want to see essentially the cycle on the pH diagram.
Also, what about uncertainty for this slab?
So uncertainty, that's a good question. Should be outlined in the lab handout. I forgot to include it in here, so you'll have your typical uncertainties for, you know, the pressure reading, so make note of the smallest mark on the gauges. And then I think the lab handout has uncertainties for like the temperature recording through the data acquisition system. I don't remember what it is off the top of my head. And then calculating the uncertainties should be fairly straightforward, because if you remember, our energy equation was just like Q dot is equal to a difference in that.
Okay, yeah,
Yeah,
that
so,
makes sense.
yep, other questions? No? All right, cool. Well, good luck.